Good morning, student. Welcome to TYBSc Organic Chemistry lecture. Myself, Dr. Kailas Labhade, Associate Professor, Department of Chemistry, S.V.K.T College, Devlali Camp, Nasik. During last lecture, we have started rearrangement reaction. In that lecture, we have seen what is rearrangement reaction, different types of rearrangement reaction. Then we have seen intermediate involved in rearrangement reaction, and finally we have seen Beckmann rearrangement. As you all know, the rearrangement reactions are the reactions in which carbon skeleton or functional group of the molecule undergo changes. In some cases, both carbon skeleton as well as functional group are going to change. We have seen different type of rearrangement reaction. In that, 1,2 rearrangement reaction is the major type of rearrangement. Then we have seen pericyclic rearrangement. In pericyclic rearrangement, there is simultaneously movement of sigma as well as pi bond taking place. Then we have seen olefin metathesis. In olefin metathesis, exchange of alkylidine group between two different alkene take place. We have seen different intermediate that are involved in rearrangement reaction. In that case, we have seen carbocation intermediate, we have seen nitrene intermediate, we have also seen oxonium intermediate. And finally, we have seen Beckmann rearrangement. In that case, ketoxime undergo rearrangement to produce amine as a product. Now in today's lecture, we are going to see 3 different rearrangement reactions. In that, first is Beer-Villiger rearrangement reaction, second is Fevroski rearrangement reaction, and third is Curtius rearrangement reaction. Learning objective of this session: at the end of this session, students should understand mechanism of Beer-Villiger rearrangement, mechanism of Fevroski rearrangement, and mechanism of Curtius rearrangement. They should able to write the mechanism of all these 3 rearrangement. The use of this rearrangement in organic synthesis is very important. That's why at the end of this session, students should able to use these rearrangement during organic synthesis. Now, first rearrangement, that is Beer-Villiger rearrangement. This rearrangement was discovered in 1899 by Beer and Victor Villiger. Treatment of ketone with peroxy acid give an ester or lactone from cyclic ketone. It is also called Beer-Villiger oxidation. In Beer-Villiger oxidation or Beer-Villiger rearrangement, there is oxygen insertion. For example, here ketone molecule is shown, and when this ketone react with per acid, there is formation of ester. When cyclic ketone is there, it undergoes same reaction and there is formation of lactone. These are some features of Beer-Villiger rearrangement. Anti-periplanar orientation of migrating group and leaving group favors the migration. Means the group which is going to migrate should present anti-periplanar with the other group. Common per acid used for this reaction is perbenzoic acid, peracetic acid, metachloroperbenzoic acid, peroxy trifluoroacetic acid. These are some acid which can be used for this rearrangement reaction. Under Beer-Villiger oxidation condition, aldehydes are converted to acid. That's why they are not undergo Beer-Villiger oxidation. Let's see in this case aldehyde that is converted to acid with the help of per acid. Let's see the mechanism of Beer-Villiger oxidation reaction. This is the ketone molecule. Ketone on treatment with acid. We know that oxygen carries electron pair. That's why protonation of this oxygen is taking place. OH positive group is formed. this bonding pair of electron can be shifted on this oxygen. Now, this is the resonance structure of this structure. In this case, there is electrophilic carbon atom. The per acid have molecular formula RCO3H. This oxygen has electron pair. These electron pair can be utilized for the initiation of the reaction, and after addition of these two, we get this intermediate. Finally, in Beer-Villiger oxidation, we get one molecule of ester and another molecule of acid. Now, let us see acetone to methyl acetate conversion. This conversion is carried out by using Beer-Villiger oxidation reaction mechanism. First of all, acetone on treatment with acid undergo protonation, and there is formation of this type of intermediate. This is the anion of per acid. It attack on the electrophilic center of this molecule, and another intermediate is obtained. After that, migration of this methyl group from this carbon to oxygen is taking place, and finally we get these two products. One product is ester and another product is acid. Hence, we can convert acetone to methyl acetate by using Beer-Villiger oxidation reaction or Beer-Villiger rearrangement reaction. In this case, oxygen is inserted between carbonyl group and carbon atom. Now, this is migratory aptitude. Migratory aptitude means the group which is going to migrate, that is migratory aptitude. When more than one groups are present, we have to use this migratory aptitude. In migratory aptitude, when there is tertiary alkyl group is present, it migrate earlier. Then this is the order of migratory aptitude: tertiary alkyl greater than cyclohexyl, greater than secondary alkyl, greater than benzyl, greater than phenyl, greater than secondary alkyl, and finally there is methyl. Means if tertiary alkyl group and phenyl groups are present, then tertiary alkyl group is going to migrate. The most electron rich alkyl group migrate most readily. Migrating ability of alkyl group increases if electron donating group is present. For aromatic compound, if electron donating group is present on aromatic system, then migrating ability also increases. Let us see stereoelectronic effect in Beer-Villiger oxidation reaction. There are two types of stereoelectronic effect. First is called primary stereoelectronic effect. In this case, anti-periplanar orientation of migrating group and leaving group is considered. Let us see in this diagram, this Rm is the migrating group and this is the leaving group. Now, there is anti-periplanar orientation of these two groups is there. Second effect is secondary stereoelectronic effect. Anti-periplanar alignment of the lone pair of electron on the oxygen is considered here. This is one lone pair of electron and this is another lone pair of electron. These are the stereoelectronic effect which are interested or which are utilizing in Beer-Villiger rearrangement. Now, this is the example. In this example, migration of alkyl group taking place, and with migration of alkyl group we get a product with retention of the configuration. In this case, chiral carbon is present and starting compound having R configuration and final product is also having R configuration. Let us see how mechanism of this reaction is taking place. As you know that the oxygen having electron pair, this electron pair attack on this hydrogen which is the part of this per acid. Then this OH positive is formed, carbanion or conjugate base of that per acid is used for attack. This intermediate is obtained, and migration of this group from carbon to oxygen gives two product, means this intermediate compound is break down into two part, one is ester and one is carboxylic acid. In this case, migration of alkyl group occur with retention of configuration. Starting compound as well as product both has R configuration. Now this is the another example. In this example, cyclohexyl methyl ketone is the starting compound. It react with perbenzoic acid. Beer-Villiger rearrangement reaction is taking place, and as usual conjugate base of this perbenzoic acid attack on this electrophilic center. This intermediate is obtained, and after obtaining this intermediate, cyclohexyl group migrate from this carbon atom to oxygen. In this case, two groups are present, one is methyl group and another group is cyclohexyl group. In this case, cyclohexyl group get priority for the migration, and your final product is cyclohexyl acetate, and the side product is benzoic acid. Let's see another example of Beer-Villiger oxidation or Beer-Villiger rearrangement. In this case, cyclopentanone is converted to delta lactone, means there is increase in ring size. In this case, the mechanism is like this: oxygen atom get protonated with H plus from that per acid. After that, this carbon become electrophilic in nature. Conjugate base of per acid attack on this electrophilic carbon. This intermediate is obtained. There is migration of the bond taking place in this case, and 5-member ring is converted to 6-member ring, and this lactone is the product which is obtained in this reaction. Now this is the another reaction in which it is shown that which bond is going to cleave during the formation of the product. Let's see this compound containing two group, one cyclopropyl ring is there and another benzene ring is there. As usual, protonation of this oxygen is taking place. After that, conjugate acid of this per acid attack on this electrophilic center, and there is formation of this intermediate. In this case, this benzene ring migrate from carbon to oxygen to give the product. This is the main product, which is ester, and this is the acid. Trifluoroacetic acid is the side product which is obtained in this reaction. Let's see next example. In this case, 4-methoxyphenyl phenylmethanone is the starting compound. It undergo Beer-Villiger rearrangement with per acid, and there is formation of ester. Mechanism is very similar to earlier cases. Protonation of oxygen with per acid taking place. There is generation of electrophilic center. Conjugate base of this per acid attack on this carbonyl center, and this is the intermediate which is obtained. In this case, out of these two group, the phenyl ring which containing methoxy group is migrated. We have earlier seen that the group or the ring which containing electron donating substituent is going to migrate. This is the case here. This is the phenyl ring, and this is another phenyl ring that containing OCH3 group. Because of high electron density, this group migrated, and there is formation of ester, and another side product is obtained, that is trifluoroacetic acid. Dear student, let's see another rearrangement, that is Fevroski rearrangement. This rearrangement was discovered by Russian chemist Fevroski In Fevroski rearrangement, alpha haloketone on treatment with strong base like hydroxide or alkoxide undergo rearrangement and produce carboxylic acid or its derivative via cyclopropanone intermediate. These are some reactions that showing how that compound is converted. In this case, alpha haloketone is shown. It react with NaOH and there is formation of corresponding acid. When this alpha haloketone react with sodium ethoxide or sodium methoxide, there is formation of corresponding ester. In first case, acid is formed because we use NaOH or KOH as a base. In second case, we get ester as a product because in that case we use sodium ethoxide, sodium methoxide and other methoxy or ethoxy derivative of sodium. Now in case of cyclic alpha haloketone, there is ring contraction is possible. This is the example. In this case, 2-chlorohexanone is the starting compound. It reacts with sodium hydroxide. It undergo Fevroski rearrangement and there is formation of the compound which containing 5-member ring. In next case, the starting compound is 5-member ring, that is 2-chloropentanone is the starting compound. When it reacts with sodium ethoxide, corresponding ester is formed. In that case, 5-member ring is converted to 4-member ring. In this case, ring contraction is taking place in Fevroski rearrangement. This is the mechanism that showing how that Fevroski rearrangement is taking place. Base abstract the alpha hydrogen atom because alpha hydrogen atom is more acidic hydrogen atom. That acidic hydrogen atom is taken by base and there is generation of carbanion. Carbanion can be converted to enolate and after formation of enolate, there is formation of cyclopropanone intermediate. Another molecule or another anion of base, that is OH minus, attack on that carbonyl carbon and ring opening taking place. Opening of ring is take place in such a way that it should produce more stable carbanion. After protonation of carbanion, we get final product. These are some feature: abstraction of alpha proton and formation of carbanion or enolate is taking place in first step. Then formation of cyclopropanone ring intermediate is there. Then opening of intermediate by attack of base, generation of corresponding anion, and finally that corresponding anion is protonated by water or the solvent. Let's see another reaction that's showing the mechanism of Fevroski rearrangement. This is the alpha hydrogen atom. This is your functional group, that is carbonyl carbon, and this is alpha halogen, that in this case it is chlorine. First of all, base, in this case OCH3 act as a base. Base abstract this proton and there is generation of carbanion. This carbanion can be converted to enolate or this carbanion can attack on this carbon. There is formation of cyclopropanone intermediate. This 3-member intermediate is formed. Then OCH3, that is the base that attack on this carbonyl carbon, opening of this carbon oxygen bond taking place, O minus is formed. Now when delocalization of this negative charge is taking place, this ring is going to open. Opening of ring should be in such a way that it should produce more stable carbanion. In this case, as it is symmetrical molecule, ring opening can be take place from any side. After ring opening, we get this carbanion as an intermediate. It abstract proton or it take proton from solvent or water, and finally final product is obtained. This is another example. In this case, 6-member enone or 6-member ketone is converted to carboxylic acid. In this case, ring size is contracted, or 6-member ring is converted to 5-member ring. Let's see, this is alpha proton. It is acidic proton. Base take this proton. There is formation of carbanion. This negative charge can be delocalized through this carbonyl group. After delocalization, cyclopropanone intermediate is obtained. Now base attack on this carbonyl group and ring opening is taking place. Once again, this is symmetrical molecule, that's why ring opening can take place from any side. There is generation of another carbanion. This carbanion take proton from water and there is formation of final product, cyclopentane carboxylic acid. This is another example. In this case, alpha haloketone is converted to corresponding ester with sodium ethoxide or sodium ethoxide. In this case, once again alpha proton is abstracted by that base and there is generation of carbanion, enolization is taking place, and finally there is formation of cyclopropanone intermediate. This cyclopropanone intermediate undergo reaction with base attack on this carbonyl group and ring opening is taking place. After ring opening, there is formation of carbanion and this carbon take proton from water or the solvent which is present in reaction medium. The direction of ring opening of cyclopropanone is determined by the most stable carbocation formed in the reaction. As we have already seen that ring opening is taking place in such a way that after ring opening there should be more stable carbanion should be obtained. Now let's see this example. In this example, two different molecules are there. This is 1-chloro-3-phenyl-2-propanone and this is 3-chloro-3-phenyl-2-propanone. Both are different molecule, but same intermediate is obtained in this case. After abstraction of alpha proton, same intermediate is obtained. Now OCH3 minus attack on this carbonyl group. In this case, ring opening is taking place only by one way. When this bond is broken to open the ring, carbanion is generated on this carbon and this carbanion is stabilized by the resonance effect, means this negative charge can be delocalized inside this benzene ring. That's why this is the stable carbanion. If the carbanion is generated at this place, it is not stabilized by delocalization in that benzene ring. That's why this carbanion which is generated is more stable and hence more stable carbanion is generated during Fevroski rearrangement. This carbanion abstract proton from that methanol and final product is obtained. In some cases, intramolecular substitution can be take place and this is the example in which intramolecular substitution is taking place. This is alpha haloketone, this is alpha carbon and at here chlorine atom is there. On treatment with sodium methoxide, this acidic proton is removed and there is generation of carbanion. This negative charge is used for further reaction and there is elimination of Cl, cyclopropanone intermediate is obtained, and again treatment with OCH3, ring opening is taking place in such a way to produce more stable carbanion and finally protonation of that carbanion produce this compound. In this case, this Cl group which is present here is replaced by CH3 group, hence we can say that this is substitution reaction. But this substitution reaction is taking place via 3-member cyclopropanone intermediate, and hence it is Fevroski rearrangement. Now, quasi-Fevroski rearrangement. Ketone which does not have alpha hydrogen atom undergo a benzylic type of rearrangement and produce the product which is similar to Fevroski rearrangement, and that reaction is called as quasi-Fevroski rearrangement. Let's see this example. In this case, there is no alpha proton. This is your functional group. This is alpha carbon. At alpha carbon there is no proton. This is another alpha carbon. At this carbon also there is no proton. That's why there is no alpha hydrogen atom is present in this substrate molecule. When base attack on this carbonyl carbon, this intermediate is obtained, and in this case this phenyl group migrate from this carbon to this carbon. Simultaneously elimination of bromine is taking place, and there is formation of final product which is ester. This is another example that is also showing quasi-Fevroski rearrangement. In this case also there is no alpha hydrogen atom. Let's see here, this carbon does not show alpha hydrogen. In this case also there is no alpha hydrogen atom. On treatment with OCH3, that is methoxy group, this intermediate is obtained. Once again there is migration of benzene ring is taking place, and finally this product is obtained. Now next rearrangement reaction, that is Curtius rearrangement. In Curtius rearrangement, thermal conversion of an acyl azide to an isocyanate via nitrine intermediate is taking place. Reaction, in this reaction isocyanate is formed. This isocyanate is attacked by a nucleophile, that is water, and amine and alcohol gives primary amine, carbamate and urea derivative respectively. In this case, this is acyl azide, RCON3 is acyl azide. When it is treated, when it is heated, there is loss of nitrogen gas, there is formation of isocyanate, and this is the intermediate which is obtained during Curtius rearrangement. On treatment with alcohol, there is formation of carbamate as the product. When it is hydrolyzed by water, there is formation of amine, and when another amine is used for the reaction, there is formation of urea derivative. Hence in Curtius rearrangement, we can prepare this type of product by using different solvent which react with that isocyanate. When alcohol is there, there is formation of carbamate. When water is there, there is formation of amine, and if we use primary amine, then urea derivative is formed. Now the substrate molecule for Curtius rearrangement is acyl azide, and this reaction shows how that acyl azide is formed. It can be obtained from carboxylic acid. Carboxylic acid on treatment with thionyl chloride, that is SOCl2, produce acyl chloride, and this acyl chloride on treatment with sodium azide produce acyl azide. Another reaction in which carboxylic acid directly converted to acyl azide by using DPPA reagent. In next case, this carboxylic acid is converted to corresponding hydrazine by reaction with hydrazine. This is acyl hydrazine which is obtained, and this acyl hydrazine on treatment with nitrous acid produce acyl azide. Now this is the mechanism of Curtius rearrangement. Acyl azide is shown, the lone pair which is present here that are utilized for the reaction. This R group present is migrated from this carbonyl carbon to this nitrogen group. there is formation of isocyanate as intermediate. After that, there is formation of amine as the main product. Along with that, carbon dioxide is also formed. This is the reaction in which benzoic acid is converted to aniline. Benzoic acid first of all react with thionyl chloride, and there is formation of this acyl chloride derivative of this benzene. It react with sodium azide, acyl azide is formed. Then rearrangement taking place, this phenyl ring or benzene ring migrated from this carbon to electron deficient nitrogen. Isocyanate is obtained. Isocyanate on reaction with water, that is hydrolysis of this isocyanate, produce aniline and carbon dioxide as a product. This is another example in which carboxylic acid is converted to ester. Carboxylic acid react with, that is another reagent, in refluxing toluene there is formation of acyl azide. The reagent which is shown here is PH2O twice PON3, and here the rearrangement is taking place. Isocyanate is obtained. This isocyanate on treatment with tertiary butyl alcohol produce tertiary butyl ester as a main product. This is the example in which acid is converted to amine by using Curtius rearrangement. Acid is given, reagents are given, and product is also given, and we have to give the mechanism for this reaction. First of all, that acid is converted to azide, and after formation of azide, the migration of group taking place, and there is formation of isocyanate. Isocyanate on treatment with water, there is formation of amine. Let's see assignment for today's session. First question, explain mechanism of Beer-Villiger rearrangement. Explain Cauchy-Fevroski reaction. And third one, how aniline is prepared from benzoic acid by using Curtius rearrangement. You have to solve all these questions and send me on my Google Classroom. Summary of today's session. We have seen Beer-Villiger rearrangement reaction. In Beer-Villiger rearrangement reaction, peracid is the reagent which is used. It is also called Beer-Villiger oxidation reaction. In this case, ketone is converted to corresponding ester. There are different catalysts used in Beer-Villiger oxidation reaction, that is metachloroperbenzoic acid, peracetic acid, and all other peracid can be used. In some cases, ring contraction is taking place. We have seen Fevroski rearrangement, we have seen Cauchy-Fevroski rearrangement, and finally we have seen Curtius rearrangement. We have seen synthesis of amine and ester by using Curtius rearrangement. In next lecture, we are going to see the mechanism and application of remaining rearrangement reaction. In that case, we are going to see pinacol-pinacolone rearrangement. We are going to see glycine rearrangement. Thank you.